So today we'll start going over the current mode control. And the second technique will be current mode control. It's a bit of a history behind this. Early 90s, current mode control appeared in which both voltage and current could be monitored. So in the previous technique, we only monitor voltage, right? And we already saw the drawbacks of doing this, especially when the change happens at the input voltage. So then what can they do? What can we do to improve this, right? So why not add another loop, inner loop, right? A smaller loop that would look at the change, not the change, sorry, that would look at the current through the inductor, conceptually, current through the inductor. But in practice, you could actually sense current through the switch, sense currents through the diode, because all three represent the same peak value, right? Under CCM, maybe use empty or blank page. Under CCM, continuous connection mode, right? The inductor current will look something like this, right? Charging, discharging. Assume these are all symmetrical. Charging, discharging, right? So what current mode control does is that it keeps a watch on this peak value, right? It watches that peak value, right? If it hits a certain threshold voltage, then it will turn off the switch inside the controller. We'll see later on, right? Now, since it is using the peak current of the inductor, right, peak inductor current, to provide the controller action, therefore, I don't have to use inductor current, right? I could also use switch current, right? That, right? Let's just do it one more. See? Or you could also use diode current. This is the switch current. And you could also use the diode current, right? If you have a buck converter, of course, right? This is the same for buck boost and buck boost. Buck boost and buck boost. The shape is the same for all three. So I diode right here, and this is I current. Actually, going that way, okay? So switch current, I switch right here, I diode right there. So I switch is like that, just it's shapes just like that. And then I diode shaped just like this, right? Something like this, right? So again, since current mode control again monitors the peak current, then we can see that that peak current is the same as that peak current is the same as that peak current, right? So conceptually, though, what we want is to monitor the inductor current, but in practice, we actually could use the switch current as well as the diode current, right? I rarely see controller um, utilizes inductor current for current sensing of the current mode. Now, um, there are a couple of advantages of doing this, right? I'm gonna change to synchronous, change the buck to a synchronous buck, like that. So instead of diode, I replace it with another MOSFET. Right? But there is an advantage, or at least a couple advantages of using either switch current or diode current compared to inductor current. Okay? Can you think of at least one advantage of why in practice we use either switch current or diode current to sense the same peak current? Anybody?
Because they share the peak.
Yeah, but why is it more advantageous to use switch current rather than inductor current?
Is the switch or the diode might be referenced to ground?
That's correct. Right, exactly. So you can see that that's one advantage. If you sense this current right here, right, then let's say for sensor, this is one I did not mention. Typically we use resistor, right? So small resistor. So if you use sensing resistor, then imagine you have to measure two different voltages, right, to get the information of that peak value, right? Because you want to convert from current to voltage, right? That's why you use sensing resistor. But imagine if the resistor is over here, then you only need one voltage because the other voltage is ground, 0, right? So simpler circuit, right, to implement the sensing. That's number one advantage. What is the other advantage?
The switch is more on the input side than the inductor.
Good point. It's closer to the input, but both of them I will actually right away. Both of them contain the same information, right? So as soon as the input voltage changes, inductor current slope will also change, right? So even though it's connected to the inductor, it would actually be as fast as sensing it here, right? Just the first time it sees the change in the input voltage, it would directly be seen by the inductor, right? Because by KCL, as you can see, IL is equal to I switch plus I diode. So any change in the upslope here, it would also be reflected right away to the inductor current. Does that make sense? So therefore, it's as fast. But the other disadvantage has to do with the resistor as well, is that if you use inductor, then you actually sensing the current, you're actually sensing the entire inductor current, right? I'm going to shade this. Right, well, you get the idea, right? So the entire inductor current. Whereas if you're sensing switch current or diode current, you're only sensing a portion of the current. See that? Only a portion of the full current. Why is that important? Why is that what do you call it? An advantage by only sensing a portion of it. It contains the same info, but we are sensing only a fraction of the full current. Why is that an advantage? My hint is this resistor. What is it?
Oh, the resistor has less power dissipated through it.
Very good. That's why, right? So by not sensing the full current, you can see the shade there, right? Instead of sensing, this entire trapezoidal current right here, right? Imagine this entire current flows through the resistor compared to just a portion of it, right? I'm kind of exaggerating here. The height to be as high as this one, as tall as that one. But imagine that, right? So therefore, the fraction of the current, which still contains the same information, would dissipate less power to that resistor, to that sensing resistor, right? So two advantages, okay, of sensing the current that contain the same peak value either on the switch or on the diode, right? Number one, reference to ground, right? So in this case, for a buck converter, it's going to be the synchronous switch, and then the other advantage would be more efficient sensing. Okay. Any questions? All right. Yeah, so the inner loop senses peak switch current, as I said earlier, right? Now, even here, I put switch, but again, conceptual is actually inductor that we want to sense, right? Conceptually. Oops. All right. Back then in early 90s, it was not widely used because if you want to implement current mode controller or current mode technique, then you have to add all of these circuitry by yourself, basically discrete components, right, to add to the voltage mode, right? So it's a hassle to do that, right? But then this company called Unitrode, right, and this is a legacy part. They were the first who were able to manufacture or produce this controller that provides current mode control, right? It's called the UC18 family. 1846 is one example of it, right? So if you talk to some experienced power supply engineers, they would know this, right? UC1846. This is actually the first current mode controller I used. Designing my first power supply, I used this controller, UC1846. And of course, nowadays there are variations of, not variations, but the same controllers that have the same features as the UC1846 and even more, right? So now we have different manufacturers who actually make similar to UC1846. UC1846 obsolete, of course, right now, but nowadays they make a better ones, right? Better than UC1846, but the same basic function. Right? Unitrode, the company themselves got acquired by Texas Instruments. So for those of you who would be working for Texas Instruments, once you start working there, you can ask about, Unitrode is out in the East Coast. I don't remember which state, maybe Massachusetts, I don't know, but they're in the East Coast. If you go to the rotation program, you can be stationed there in the East Coast. All right. So UC1846 can be used where 280 degrees out of phase pulse width modulated output could be provided, such as for push-pull, half-bridge, interleaf forward, and interleaf flyback. Nowadays, current mode controller ICs are quite common. In fact, I would say most of, right, maybe 90% of controllers that you see out there would be current mode. And it's very rare now to see voltage mode. There's still some, but it's quite rare nowadays. Uses error voltage to directly control the peak of the switch current. Ramp is derived from the inductor current waveform. So in voltage mode, right, the ramp right here, the ramp right there, right, that's internal to the controller, right? So we produce or we make that ramp internally in the controller. See that right here through the oscillator, right? We make the ramp. Here, instead of making our own ramp inside the controller, we use the inductor current ramp, right? As the control voltage, right? So that's one of the differences. Where is it? Oh my God, I don't know why it keeps scrolling that way. Yeah. So ramp is derived from inductor current waveform. Remember I said earlier, conceptually, we want to sense the inductor current. The reason for it, because again, we want to create the ramp from the inductor current, right? But that same ramp can be generated from the switch current, right? Or the diode current. And then uses error voltage to directly control the peak of the switch current. So the error voltage, remember the error voltage? The output of the feedback voltage right here. The output of the feedback voltage compared to the reference voltage, that gives us the control, the error signal. Again, I should call it VC to be consistent, but here they're actually consistent. VEA, VEA. right? So this right here defines the limit of the peak of the current through the inductor. See, I'm drawing it with inductor. Again, this is a concept, right? So you put the sensing there, right? You sense the inductor current, and the peak of that inductor current is limited by the error signal coming out of this amplifier, right? So right there, that defines the time when the switch has to be off, right? So imagine in steady state, right? So in steady state, you're going to have constant error signal, right? Because it's steady state. So the error signal will be constant, just like I draw right here. And you have the clock, just like before, you have the clock, right? And then given that constant error signal, and you sense the inductor current, right? From the low value, right? It increases, charges, right? The current is charging, the inductor is charging. And right when it hits the error amplifier voltage, output voltage, that's why you compare it right here. See this? You compare the two again. So you compare the voltage coming out of the inductor current with the output of the error amplifier. Once the voltage from the inductor current hits that error signal voltage, then that's how we define turn off of the switch, right? So as long as inductor current, which is represented by this voltage, IL times RS, is less than EA, less than the output of the, less than the error signal, so as long as the sense current voltage, the sense inductor current, right, which is translated to voltage, is less than error signal, then keep the switch on, right? Once it hits that threshold, that limit right there, then turn off the switch, right? So now it discharges. Okay. Any question on this? Any question on this? And then how long, or not how long, but what determines when this discharging stops? As you can see, the discharging stops when the clock ensues, right there. Okay. So the charging stops by the error signal. The discharging is stopped by the clock signal. Right? Any questions? So conceptually, that's what's happening inside current mode control technique. As I said earlier, error amplifier output PC. Again, sorry, I use different naming. I'm going to have to fix this for future version. I keep using VC and EA. These are all the same, okay? VC and VEA. Let's see what's next here. The PWM comparator will output high, as I said earlier, until the sense inductor current equals the control voltage. Okay, so I've already explained that one. While at steady state, okay, if VC increases, what is VC again? That's the error signal, right? That's the VEA. That's the output of this right there. That's VEA, which is again the same as VC. When, what did I say? Well, at steady state, if VC increases, how can you get VC increasing? Well, that happens when the output voltage drops, right? Right. So when the output voltage drops, there you go. When the output voltage drops, of course, V out prime drops. So therefore, the difference between Vref and sampled output voltage becomes bigger. Right? Oh, sorry, no, is it bigger? Yes, becomes bigger. So that would cause duty cycle to increase. Right? Why? Remember in in voltage mode, if this happens, actually, no, that's not this one. Sorry, forget that. In the voltage mode control, when the output voltage changes, then the controller will also see it right away, right? In the voltage mode control. So let me repeat. For voltage mode control, when the output voltage changes, then the controller will see it right away because it is monitoring the output voltage, right? So let's do the same thing for current mode. Will the current mode do the same thing? Most definitely, right? Because we still monitor the output voltage through this voltage divider. So as the output voltage drops, right, VC, this voltage, increases, right? Remember VC, VC represents the limit of this peak of the inductor current, right? So this is before the change in the output voltage. Let's say VC is right here, but then all of a sudden, let's say the output voltage changes right away. As soon as the output voltage changes, VC increases. See that? Increases to this much, to this value, to the new value, right? VC new, right? Okay. And let's see if this actually increases to the cycle, because that's what we want, right? Output voltage drops, we want duty cycle to increase right away, right? So with current mode control, output voltage drops, DC increases. That way, that means the limit for the inductor current peak also increases, right? So watch. Input voltage is still the same, right? So therefore, the charging slope, right? You can see actually will also change because the charging slope is V in minus V out. So the charging slope should be higher now. So this should be steeper a little bit, right? But then, yeah, because it is steeper a little bit, so it'll be faster. It'll be faster to charge. But then the faster slope is compensated by the increase in VC, right? Because it is faster. If I imagine if I keep the same limits right there, because this is faster, so therefore the duty cycle will be smaller, right? Imagine that, right? Imagine if this slope is faster, then it will be faster to reach this limit. That means the duty cycle will be smaller. Make sense? Imagine if this is faster, right there, then the duty cycle becomes smaller. But how do we compensate for that? So in current mode control, as soon as VC increases, so would be the limit for that peak. So even though this is faster, I don't know if I draw it correctly here, but assume this is faster slightly, right? The slope is getting faster slightly. So then it will take more time for this charging slope to hit that limit, right? Longer time means bigger duty cycle, as we expected, right? This is what we desire. Voltage drops, but we want the controller to see it right away, and it did, right? It does it, right? It does see it right away, right? By increasing VC. Pretty cool, right? So by increasing VC, simply by increasing VC corresponding to the drop on the output voltage, you can increase duty cycle, right? To compensate for the faster charging slope. Any question on this? All right. Now, that's what happened with voltage mode as well. So there's no difference there, right? Different way, different mechanism on compensating for the drop in the output voltage, but they both are doing the same thing, right? They are fast. They are both fast in responding to a change in the output voltage. But what about when the change is in the input voltage? Remember, this is the disadvantage of voltage mode, right? How could current mode control improve it? Well, let's check this out. Okay, let's go through this. That's the second case right here. While at steady state, if input voltage Vin drops, so now input voltage drops, while output voltage stays the same, right? If output voltage stays the same, that means VC stays the same, right? Remember that picture again? I'll draw it again. So you can see if output voltage does not change or stays the same, of course, VC would stay the same, right? And what does VC define in our current mode controller? VC defines a peak of the inductor current. See that? So if I go back to this picture, right? Input voltage changes, output voltage stays the same. So VC right here stays the same as well, just like these two cycles right here, right? VC stays the same. But we want the controller to take action for this, right? Because we know a change in the input voltage, right, would cause a change in the inductor current, right? Remember this? So I have to go back and forth between the two. I don't know if you remember this one right there, right? The change in the input voltage for the same output voltage will change the charging slope, because the charging slope is V in over minus V out, right? So now it becomes smaller, right? If V in is dropping, right? So if V in drops, right, that means DIL dt, the slope during on time, charging slope will be V in minus V out over L, right? So if V in drops, V out is the same, that means the slope would be slower. You can tell from here, right? This slope is faster, that slope is slower. And again, the implication is that if the slope is slower, you keep the same duty cycle, then you get the same, you get less average current. See that? Which in turn, it will take some time before then this current then will be sent to the output resistance. Now the control will see it, right? So it's not being seen right away by the controller for voltage mode control. However, let's take a look at current mode. How is it better? Now, while at steady state, if input voltage V in drops while output voltage stays the same, then VC stays the same. That could be a problem, but we'll see. However, the charging slope of inductor current changes as well, as I explained earlier, right there. That's the same equation I wrote earlier, right? This in turn increases the duty cycle until VC is reached. Why is that? So what I'm trying to say here is that if there is a change in the input voltage, in this case drops, right, in the input voltage, we want duty cycle to increase, right, for a buck converter, right? So duty cycle is equal to V out over V in for a buck converter, right? So if V in drops, then of course we want duty cycle to increase, right? So will this controller do it right away? The answer is yes, right? Because this change in the charging slope means it will take more time to reach VC, right? So how do I do this? Maybe blank page. Do I have a picture? Maybe I have a picture. Oh, yes, I do, right here. Awesome. So right here, this actually represents that case, right? The first two cycles, nothing happens there, right? You can see VC stays constant. So there is no change in the output voltage, right? No change in output voltage. That is represented by this constant VC. Good. Now, this, however, slope represents what? The IL dt represents V in minus V out over L, right? So now you can see that these two right here, this slope and that slope, charging slope, are the same. That means there is no change in the input voltage, but watch this one. You can see that one is slower, right? I don't know if you can see, hopefully, yeah, it is, right? So This slope right here, call it slope number 2. This is slope number 1. This is slope number 1, right? They're both the same, but if you look at slope number 2, it's slower, isn't it? Slower means for the same output voltage, because this, how do I know it's the same output voltage? Because VC is constant right there. So output voltage is the same, but if the slope is slower, that means, well, L is fixed. That means V in must be dropping. So this represents slower slope, right? Represents drop in input voltage, right? And what do I want? What do we want when input voltage drops? We want duty cycle. We want duty cycles to increase right away. We don't want to wait like the voltage mode control. It has to wait until the average current changes, right? And then it's sent to the output voltage. Here, as you can see, right away the controller sees it, right? Because again, the drop in input voltage means the slower the duty cycle. For the same limit, the same threshold, the slower the duty cycle, the longer it takes, right? The longer the current takes to reach its peak value. Longer time means bigger duty cycle. Right away, right? The change happens right here. The in drops. Right away, the controller sees it. See that? Bigger duty cycle. Compared to voltage mode, right? In voltage mode, still stays the same. Where is it? Oops, right there. You see, duty cycle still stay the same. Still, right? That's when V in drops. But duty cycle already, the duty cycle stays the same until the current goes to the output. In current mode, right here, V in drops right there. Right away, duty cycle already increases. Cool, isn't it? So that's how current mode control is better, right? In order to compensate for both a change in the output voltage and a change in the input voltage, right? So I already demonstrated to you that if the output voltage changes, then the duty cycle changes right away. If the input voltage changes, then the controller will see that right away. Awesome, right? Any question on this? That's kind of the block diagram of a circuit, simplified circuit diagram of current mode control. You can see the output voltage monitor, right? Sensing and the current sensing of the inductor. Again, conceptually, you want to sense the inductor current. And yeah, you can see the output voltage is being compared with the VREF, and then you have the VC output. Remember the constant output, right? The limits of the peak, and you compare it with the slope, right, of the inductor current. Notice that there is another input. You see this? There's another input. Slope compensation. What in the world is this slope compensation? Why is it there? Right. So far, I only spoken of. I've already spoken of these two, right? The third one that's coming up. Okay. So we'll go over this either today or on Monday. We'll see. Okay. All right, and then that would output PWM, right? And then turn the switch on and off. All right. Any questions? Body plots of this current mode is also better, right? If you look at, which means it's easier to compensate. If you compare the two, voltage mode versus current mode, you see the difference in the gain plot, right? Look at the roll off right here, right? It's minus 40 dB for voltage mode and minus 20 dB for current mode. This means there is a single pole right here and there's a double pole right there, right? As we already know, right? Why is it good to have minus 20 dB? Look at that would correspond to the phase angle, right? Minus 20 dB or a single pole means you only have minus 90 degrees, right? Change in the phase angle, whereas minus 40 dB gives you minus 180 degrees, right? Phase angle. That would be the lower angle, the minus 90 degrees. That's actually good for phase margin, bigger phase margin than the minus 40 dB, the 180 degrees phase angle, right? I'll explain a bit later, but the other thing that that's good about single pole is that it doesn't have the quality factor, right? Remember quality factor that would determine how steep the change is in the phase angle, right? If the Q is high, then it will drop drastically, right? If Q is low, then it will be very slow change, right? So there's a lot of variation, right, of the phase angle depending on Q point, right? And this again would impact how phase margin is impacted, how phase margin is provided by the controller, right? Whereas the minus 20 dB doesn't have that effect, doesn't have the Q effect, right? It's going to be just like that, right? The minus 90 degrees, right? You see this boost right there is because I added a zero, but that's going to be later. Okay, don't worry about it for now. But if you ignore this for now, you should get something like this for current mode, right? So this is more stable phase margin than all of these, right? And plus it's also good, right? Because it's a boost. It's a boost in phase margin, isn't it? Let me erase this. Unfortunately, it's going to be hard to get it from here, but let me try. Let's see. What is the crossover frequency here? Crossover frequency is about 1 kilo for voltage mode. It's about 1.2 kilo. No, 1, 2, 3, about 1.2, yes. 1.2 kilo for current mode, right? So let's go to the phase plot. 1 kilo is right there. Right, for the excuse me, for the voltage mode. What is that phase angle? It's about, let's say, minus 190, something like that, right? What about current mode? That's about 1.2 kilohertz. That's about this. That's this line right there. You can see the phase angle is right there. That's minus 90 degrees, right? So that's the angle for current mode. Right. So how do you calculate phase margin? The angle at crossover frequency plus 180 degrees. Go ahead and calculate apply this equation for voltage mode. What do you get? Phase margin here, what do you get? You get minus 190 plus 180. This is unstable already. That's not good. It's minus, it's negative phase margin. Look at the phase margin for voltage for current mode. What is it? Minus 90 plus 180 degrees. That's plus 90. You can see that by using current mode, you boost the phase angles from minus 190 to minus 90. So that's a boost, basically, right? Which will be good for phase margin. I just showed you that mathematically right there. From minus 10, which is bad, right? So that's negative, to positive phase margin, which is good, positive 90. That's more than enough. As I said on Monday, typically we want to have, I believe, around 60 degrees or 57 degrees or above. Right. So you have enough safety margin for phase margin. Right. And this is already stable in terms of phase margin is already good. Right. So That's another advantage of current mode, right? That you have a single pole effect instead of double pole effect. Does that make sense? Now, why is it only single pole effect, right? You still have the same buck, right? Still have the same buck converter, right? The only thing I use differently is the controller. Now, why do you have a single pole effect? Well, because in current mode, remember we use VC, right? VC to limit the inductor current, right? Now, the effect of that is that at steady state, of this is steady state, okay? These both are steady state body plots. In steady state, if your VC is already constant, then your current the average inductor current will also be constant, right? So if this is constant, right, that means I could replace this. If the inductor current is constant, average current, I could model that as a current source, basically, right? It's not really current source, but basically you're suppressing the effect of inductance by making the current constant, right? Right. So then you eliminate the effect of the inductor by making its current constant. That means you only have one pole right there from the capacitor. Right. So that's why you have a better phase margin if you use current mode, because you're basically limiting the current. You're making the inductor current in steady state to be constant. You're forcing it to be constant based on the compensator. Not the compensator, error signal. So you'll see in some of the control circuit model of current mode, they replace the inductor with current source. Okay. Any question on this? Hopefully it makes sense so far. All right. Let's go through this and then we take a break. So those are we just review the concepts behind current mode. Right. Advantages, easy compensation, as I've explained earlier. You don't have the phase drop, that sharp phase drop for current mode. It looks like a single pole system. Improve the phase margin. I've already demonstrated that to you. And so the compensator later on, maybe next week, Wednesday, we'll talk about compensators, right? You'll see the compensator for current mode is easier than voltage mode. CCM and DCM. So CCM and DCM operation would be, we can use the same compensator basically, because in DCM, what we have is also pretty much constant inductor current. In DCM, right, it can go up and down, right? But in DCM, we use the controller that would force the inductor current to be at boundary conduction mode, right? So boundary conduction mode means constant inductor current. So the same effect, right? Meaning the inductor current looks like a current source, right? Because it's always kept at boundary conduction mode, right? Okay. So CCM and DCM operation for current mode control could have the same compensator, whereas in voltage mode it does not, right? If I go back to the body plots of voltage mode that compares CCM and DCM, you see the difference right here, right? You can see the DCM mode. The DCM for voltage mode is just like current mode, right? Minus 20 dB per decade. There is no series angle for DCM. Again, that happens because inductor current acts like a current source. Okay. So these four compensators for voltage mode will be different if you run it in both DCM and CCM for whatever reason you run in both modes. In CCM will be okay because they both can use the same compensator. Okay. Disadvantages, you have to use current sensing. That means loss. Right? This requires additional circuitry as well as some power loss. And also, with current sensing, you got to watch out for signal to noise ratio, right? Because we can have some leakage spike going through this MOSFET. So therefore, it is not uncommon to put low pass filter, right? Not just our sense, but also low pass filter before it goes into the controller, right? Just to clip the leakage spike. So the current to the MOSFET will look something like when it turns on, something like that. It's more like this actually. And so this high frequency noise has to be clipped, right? That's why you might want to put, if you have a noisy MOSFET current, make sure you put filter, low pass filter after the sensing. And then lastly, before we take a break, subharmonic oscillations, right? This is something that we're gonna go over. Is it next or no? No, it's not. Okay, that's probably after we gone through constant on time. Right. So subharmonic oscillation is an issue that is well known out of current mode control. There's always a trade-off. So one of the disadvantages of current mode control, it can generate subharmonic oscillation, especially if the duty cycle is larger than 50%. Don't worry about it for now. I'll explain this next week. Okay, I don't know. Maybe I have the time today. I don't know. We'll see. Right, but that's something that I need to explain later in the later section. Okay, so for now that will be enough for reviewing the concept behind current mode control. Are there any questions before we take a break? Yes. Okay. All right. So the next control technique is called constant on time control, COT for short. Right. Okay. Let's look at the disadvantage of current mode control. Right. In current mode control, two factors that impact the transient response performance to output load changes. So this controller right here, this type, constant on time control, attempts to address the drawbacks with current mode control, specifically this next two items that we're going to go over. The first one is that due to this error amplifier block, right here, this blue right there, right? The voltage in the voltage feedback loop, again the blue box right there, the error amplifier acts as a low pass filter. You can see there's an L, there's a C, which slows down the converter's response to any variation in the output voltage. Right, so the output voltage being sensed right away, but then there is a what do you call it? Kind of a delay because of the LC filter response, right? Here's an example. Let's see. So here is, I have an explanation on this. Yeah. Waveforms above show the effect of this error amplifier delay on the loop transient response where the load current steps from 0 amps to 20 amps with a fast slew rate. So there's a change in the current, right there. The blue right there is the change in the current. Right. And then in the bottom curve, the out drops significantly before it recovering. Okay, let's see. Let's take a look. So current goes up, output current goes up drastically, right? Sharp. So that would cause output voltage to drop, right? Yes. Why is that? I believe I explained this in EE410. Basically, you have switch, you have diode, right? You have inductor, right? You have the capacitor, and you have the load right there, right? So as soon as you do a step up in the change in the load, right? Then more currents flows, right, through these components. Agree? From what is it again? From I forgot. From 2 amps to 10 amps, isn't it? No, from 0 amps to wow, from 0 amps to 20 amps. Okay, it's even worse. So from 0 amps to 20 amps, right? It's a big change in the output current, right? So from no current to big current, 20 amps. Imagine what that does to these components, on and off, and then inductor is always on. So you're going to have some voltage drop, right? For the same input voltage, right? If the input voltage is the same, right, then the larger current means larger drop, right? Between input and output, right? Larger drop between input and output. That means what? By KVL, output voltage drops. Okay. So V out is equal to V in minus V drops, right? So bigger current means bigger drop of the voltage. Bigger drop of the voltage for the same V in gives you reduced current, right? Make sense? So that's why, as you can see here, which makes sense to me, as the current goes up, step up, right? It's a step change in the load current. It's a step up change from 0 to 20 amps. Oh, yeah, it's actually shown right here, 0 to 20 amps. You can see output voltage drops drastically, right? But this middle one, remember V comp, right? Right away, it sees that change. How do I know that? As soon as the output current goes up, right away, it goes up as well, right? Let me redraw that again, right? Keep messing up this. Okay, that's your VC. Here I call it VCOM now, right? So the output right away increases, right? Because it's this V out prime voltage drops. So the difference between Vref and V out prime increases because the output voltage drops, right? So right away it increases, as you can see. As soon as the input current increases, VCOM increases. That's good. That's good news, right? However, the controller takes action, but it takes some time to actually recover, right? So it actually takes look at it, 2 cycles, right, before it start to go up. See these 2 cycles right there? That's just kind of like staying there, right? It drops and it just stay there, right? And then it start to increase. As soon as VCOM reaches, peak value or its max value, right there, right away, this V out goes up, right? But look at the delay there, like 2 cycle delay, right? And this delay again, it's caused by the inherent there you go, inherent low pass delay, right? So that's one disadvantage. Again, in controller world, that 2 cycle delay is still considered slow, right? even though this is actually fast, right? It's actually, what do you call it, high frequency wise, this one cycle could represent maybe 10 microseconds. So 20 microseconds delay could, in their world, it's still a delay, a good delay, significant delay. That's the first disadvantage. Any question on that first? The LC filter delay. Okay. Remember, inductor is always delaying current, right? That's why, you know, Eli the Iceman, right? Inductor current lacks the voltage. So that's why it's inherently slow, that inductor. Okay. The second factor that slows down the current mode control transient response is the switching delay caused by the clock, the internal clock. Remember, we have an oscillator, right, in the voltage, both actually voltage mode control and current mode control. That oscillator defines when to start turning on or turning off the switch, right? You have that clock. Where is that? Let me show you again. Yeah, yeah, this clock right there, right? So that defines when to stop the discharging and then when to start the charging, right? Right there. So you can see that from here actually, right? So that's the clock. You can see it's constant clock time because it's constant frequency, right? If you have PWM right there, it should be a constant clock time corresponding to constant frequency. You see it? You can tell easily. Okay. That is the same clock time, right? Now this could be a disadvantage, especially when the change is introduced after we turn on the switch, I believe. Yeah. So after we turn on the switch, let's say we introduce the step change. So that's the same step change, right? From 0 to 20 amps, except if it just so happens that the change occurs right at the point where, right at the time when the switch is already on, just like you see the switch is on right now, right? Then you get a step up change, right? And right away, the feedback sees that, right? Because voltage drops, right? Output voltage drops, just like before, output voltage drops, and V comp or VC goes up. Now I call it V comp. I need to fix this. This is equal to VC. Right? So you can tell from here, look at the green waveform. It goes up right away. As soon as it sees an increase in the output current, voltage drops right away, V comp increases. That's great, right? What's not great is this. Remember the clock, right? Even though the controller sees that change already, but the controller has to wait, right, until the next clock is initiated, right, which is right here, basically, right? So that's the clock. It's the clock right there, right? You can see it's constant clocking. So because it depends on the timing of the clock, even though the compensator is already, I keep saying compensator, even though the controller is already seeing the change right there, the increase in the output of the error amplifier, the error signal already goes up, but the controller cannot do any action yet, right? Because right now the clock says, don't do anything yet, wait until the next time the clock says to turn on the power, to turn on the switch, right? So right now, all you can do is just turning off the switch, right? Instead of right away turning on the switch again, elongating the duty cycle, it would have to wait, right? Now it's just discharging the inductor again, right? What it's supposed to do is, as soon as it sees the increase in the error signal, this should go up, right? It should keep sending current to the load, right? Increase the current, right? So that you can increase the output voltage, right? But what it does is that it waits until the next clock starts. Does that make sense? So again, the change occurs right here. The in drop right here, right? That is corresponding to the increase in the current, right? But then at that time, it's already, the clock already started. So now it just wait, right? Just discharges until the next clock starts. Then you can see a big jump right there, right? You can see the big jump in the current right there, which corresponds to an increase in the voltage. You can see now the voltage increases. But in between that time, right? In between the time when it realizes there is a drop in the voltage, but it cannot do anything, right? Between this time right here, you can see the output voltage keeps decreasing, right? That's not good. Look at these two voltages right here, right? Error signal goes up. How come the output voltage goes down, right? It doesn't make sense, right? If if the error signal goes up, right? If you understand what we talked about earlier, duty cycles should go up right away, right? Theoretically, right? But then as you can see, it might happen that this change occurs when the clock already has started. Most likely that's the case, right? So even though the controller sees that, but unfortunately it cannot do anything yet. It cannot do take any action yet. That's why output voltage still is dropping, right? And that could be explained from this shaded area, right? Because what the shaded area means is that, well, this is inductor current, right? The red one, right? That's inductor current. It goes up, down, right? And then as soon as the clock starts, boom, it jumps, right, to a big inductor current. So if I draw the buck converter again, like this, like that, right? Oops. Like this. At this point, let me erase this. See, starting from that point, right? This output voltage right here is screaming to the inductor, hey, give me more current, right? The inductor right there, which is this current right there, right? So at that point, the resistor on the output says, give me more current, inductor. But the inductor cannot do that. Why? Because of the clock. The inductor says, wait, I have this clock that I have to follow, right? I have to wait until the clock starts again. So in the meantime, who do you think supply the current to the load? Anybody? Who?
The capacitor?
The capacitor has to, right? The load says, give me more current. Inductor says, wait, I cannot give you now. So who's going to compensate for that current? Of course, the capacitor. That means the capacitor has to discharge or charge. Well, you can tell it's leaving the capacitor, right? That means the capacitor is discharging. What happens when the capacitor is discharging? What happens to capacitor voltage when it's discharging? Is it going down or going up?
The voltage goes down.
It goes down. And look at how capacitor is connected to the load. They're in parallel. If the voltage across the cap is going down because it's being forced to discharge, therefore the output voltage also goes down. So you can see the reason why output voltage keeps coming down, even though the controller says, hey, increase duty cycle. But inductor cannot do that yet. So therefore, the shaded area corresponds to the energy that the capacitor has to provide, right? And by doing so, by forcing capacitor to discharge, look at the output voltage. It goes down, right? Make sense? All right. So those are the two disadvantages of current mode control in terms of transient time, right? That makes it slower compared to this next one. Okay, so this next one tries to address those concerns. Okay, Now this controller is called, or this technique is called constant on-time control, right? The control structure is very simple compared to traditional voltage and current mode control. When employing COT, the output voltage is sensed via feedback resistors. The value of the output ripple voltage is compared directly with the reference voltage to generate a fixed on-time pulse to turn on the high side switch. When the on-time pulse expires, the high side switch turns off. Okay, so the explanation is this, right? So those are just explaining it through words. But if you look at this circuit diagram, and this is the waveform that we actually conceptually implement in constant on time. And let's see if I can explain it, and hopefully it's clear. All right. So what's happening here is that it does not have that clock. Right? That's number one. That's one of the reasons why it was slow, right? Transient wise, right? The clock. So you can see there's no clock there. Interesting, right? And you can see how simpler it is compared to current mode. In current mode, you have, in current mode controller and voltage mode controller, you have two op-amps, right? You have the comparator and you have the error amplifier op-amps, right? Here you only have the comparator. So it eliminates one of the amplifiers. Simpler, right? Eliminates the clock, right? Simpler. But in addition, instead of doing that, what it does is this, right? The output voltage right here, and it's represented by this waveform right there. Imagine if this output voltage, right, the minimum value of that output voltage is compared with the reference voltage, that reference voltage right here, right? So that's why we call that, I call the value of, right? So as it's reaching, as it's discharging, right? The output voltage also goes down as the output inductor goes down. The output voltage also goes down, right? As it goes down, it finally reaches this threshold voltage, which is defined by that Vref. Then when it hits that limit, then it would trigger this pulse generator. Right? Boom, it goes out and say, hey, create a pulse. That pulse right there, you can see it's, the reason why it's called constant on time. Can you guess? Yeah, well, because these pulses are constant on time pulses. Look at the pulse width. They're all the same pulse width, right? So as soon as the voltage goes down, you know, discharging, this is charging, discharging, charging, discharging, right? Corresponding to the capacitor, capacitor charging, capacitor discharging, charging capacitor, right? As the capacitor is discharging, that means output voltage goes down accordingly, right? When it hits the minimum point right there defined by the Vref, that's the point when the controller says generate or produce a pulse and send it to the switch, right? So right there. That hit that limit, produce a pulse, constant on time, charge the capacitor again, or in this case, charge the inductor as well, right? Turn on the switch, right? During about that long, basically, right? That's the duty cycle. And then once the pulse ends, then discharge or turn off the switch, right? Hits the limit again, pulse again, right? Turn on for that long, and then when it hits the end of the pulse, discharge again, and so on and so forth. You get the idea, right? Okay, so that's the concept behind this constant on time. You can see there is no error amplifier, there is no compensator, right? COT architecture does not require the additional compensation network of voltage or current mode DC to DC control, right? So it's simpler to implement, simpler, simpler controller, basically, right? This makes the converter easier to design by requiring fewer components and eliminate the need to spend time tuning the compensator values. Tuning, so tuning the compensation, that's something that we discuss hopefully next week. Okay. Yeah, you need to have a good ramp because the ramp is generated by by this output voltage, but that could be provided by, luckily, by ESR of the capacitor. So that's, I think it could be viewed as disadvantage because ESR also introduces loss, but at the same time we need ESR for this to make sure that we have good enough ramp. See this ramp right there. Okay. What else should I say? Yeah, so let's just see how this does it, right? Well, before I do that, let's look at several points here. The COT control architecture uses the reference comparator output, as we already know, to trigger a fixed on-time pulse generator. The frequency of the pulses is determined by the output load current, right? So if the output current goes up real quickly, then of course that would correspond to a sharp drop in output voltage, right? A sharp drop in output voltage means it triggers the pulse quickly, right? Quickly and more often. Right? That's why it says right here, I believe. Where is it? So during steady state output current, the frequency is fixed, right? The frequency of the pulses will be fixed, but that's steady state. But then during a load step transient, such as the step up we saw earlier, if it's a step up, you can see the pulse will be more often, right? Because it quickly hits that the threshold, right? The value of the output voltage hits that threshold quickly if the output voltage drops quickly as well. COT control has a transient response time up to 2 times faster than the traditional voltage or current mode control. So it's fast. Lower undershoot makes it easier to meet load voltage tolerance specifications. All right, let's just look at how COT is fast or faster compared to current mode. This is the one we already saw earlier, right? Remember, it has to wait, right? Has to wait until it goes up, right? Let's see. Except I'm not sure why this is a bigger. Oh, maybe because it is such a condensed pulses. That's why it looks like bigger pulse. So that happens when. Oh no, sorry, this is current mode. Oh my God. Sorry, I'm mixing it up with COT. Sorry, this is current mode. So in current mode, it waits until the clock expires, right? So not expires, until the clock starts again. And then we have this new duty cycle, right? Bigger duty cycle, meaning bigger current. So that makes sense, right? But it takes time because it has to wait right there until the clock starts again. Now look at COT on the right-hand side. It's the same step up, as you can see, right? From 0 to 20 amps. But look how fast the output voltage follows, or try to compensate for that. See here, you have a delay, right? But over on the right side, as soon as the output current goes up real high, the output voltage drops quickly, right? And by dropping quickly, remember the threshold for the value, right? The minimum point of the output voltage hits that quickly as well. Right away, we have a pulse. Remember when it hits that threshold, means produce the pulse. Produce the pulse means turn the switch on. That's what we want, right? Turn the switch on, right? Drops again, right? Because the pulse already expires. The pulse already done. It drops again right there. That's why you see a drop. That corresponds to another drop in the output voltage and hits that threshold fast again and produce the pulse again. Produce the pulse again, right? So you can see it can recover from this drop in the voltage much quicker than the current mode control, right? Right away, it doesn't have to wait for the clock. There is no clock here, right? All it has is compare with the value of the minimum peak of the output voltage waveform. Once it hits the threshold, produce pulse, right? Pulse is only a short amount of time. It drops again, get a pulse again, right? So on and so forth. Yeah. And notice that the pulse is more often when there is a big change in the current. See that? Once it goes to steady state, then you can see the frequency is kind of constant right there, right? Almost constant frequency, pretty much constant. Over here, the frequency is high, right? Any questions on this? So that's how COT addresses the issue with slow transient time. Can you name one disadvantage, but just by looking at this picture right here of COT?
It looks like there's a minimum off time, so you can't get to 100% duty cycle.
That is correct. Yes, that's correct. But what else besides that? So yeah, it requires because the duty cycle is actually kind of related to your answer. What do you see from here compared to this, right? What do you see here? Remember, PWM is constant frequency, right? COT, as you can tell, is not constant frequency, right? So you can see the frequency of the output is not at a constant value, right? During transient time, the frequency is high. During steady state time, the frequency is fixed, right? So to me, that introduces some complication in terms of noise, for example, because now you have a noise spectrum that's all over the place, right? High frequencies and and then the constant frequencies, right? Here, the noise is only practically at one frequency and multiples of that frequency. Here, the noise spectrum is much wider, right? Which means related to the duty cycle, which means it is trickier to size the inductor, right? Because remember in EE410, we always size the inductor based on constant frequency, right? So what if the frequency is not constant? So then you base it off worst case, right? What will be the lowest frequency you can tolerate, right? So that would be corresponding to this constant frequency right here, right? So the lower the frequency gives you the bigger value of the inductance, right? Okay. So yeah, so design a component sizing in terms of inductor, that would be a bit trickier than current mode control. So this is no longer PWM, right? On the right. Any questions? So that's basically a constant on-time controller, right? Conceptually, hopefully by now you understand the difference between current voltage mode control, current mode control, and constant on-time. Are there any questions before I move on to the next one? No? All right. So this next one, I thought it should be useful to include an example of how you apply current mode control, but that's the most common one, most widely used controller these days, right? Current mode controller. And I use the one I mentioned earlier, 1843, except this one is produced by, manufactured by Micrel, right? This UC 1840 family, remember this? UC 1840X. And Micrel has the same family, right? This is one of the controllers I've used before as well, right? And here's the block diagram of the current mode controller, right? Is it 8 pins, I believe? Oh no, it's actually not 8 pins, it's more. Oh, there is an 8-pin version and there is a 16-pin version, right? These are several of the pinouts, right? You have ISNS, that's for the sensing of the current. right? Remember sensor, current sensor, it goes to this pin comp. This is where you would provide the compensator, which we have not talked about. Feedback, that's where you put the feedback from the divider, from the output into voltage divider, right? RTCT, any guess what that is? Any anybody wants to take a guess on what this one is for? No?
Doesn't that change switching frequency?
That is correct. Yes, that is correct. So that's when you can change switching frequency, right? That's an oscillator right there, but it can be driven from the external component. So depending on RTCT values, that would determine switching frequency of this controller, right? VREF is a pin that you can use for, this one can actually put out voltage. That's 5-volt voltage that you can use for any auxiliary circuit, right, that you need. Rather than having external power supply, you can just use this 5-volt power supply right there, right? But that's keep in mind, it doesn't give you that much current. Okay, so if you just want voltage, not much current, then you can use this one. I think I have an example where I use this reference pin. Okay, and on the right side we have the 2 gates signals. Remember, this is for push-pull for 2 switches. So one is on, the other one is off, right? And so on and so forth. All right. What time is it? Oh, 5 more minutes, huh? Yes. All right. So this first one, select timing resistor and timing capacitor. So that has to do with this one right here. You know what? Let's stop, because I don't think I could finish it in 5 minutes. Can I? Maybe. Yeah, let's try. So for timing capacitors and resistors, selecting timing resistor and timing capacitor, how do you do that? You need to know maximum duty cycle and switching frequency, right? And that would give you a percent dead time. And I use the word dead time, is actually off time, right? So percent off time, or in this example, I use dead time. Along with the switching frequency, we can then use the plots provided in data sheet to determine the required timing capacitor and resistor. Right? So let's say that the maximum duty cycle was calculated to be 70%. Let's just say 0.7, right? That's the max, right? And for buck converter, again, duty cycle max would be equal to V out divided by V in min, right? That gives you the maximum value for buck converter. For buck boost and buck boost and other topology, you have to look at the equation, but this is just for buck as an example. So then add 10% for to consider, take into account parasitics. So then you get, you don't have to put 10%, of course, but this is just an example. I put additional 10%, that gives us 0.8 max duty cycle. And then you can see the dead time, which is actually off time, right? Maybe in the future I'll change it to off time. Right, so on time max is 0.8 duty cycle, and off time or off duty cycle is 0.2, right, or 20%, right? Let's say the switching frequency that you pick is 80 kilohertz. Then the percent off time along with the switching frequency can be used to determine required timing capacitor. And the reason why I use, now I remember, the reason why I use that time, because that's what the data sheet is using. Instead of off time, is using that time. So keep in mind, that time right here is not the ones that you learn from synchronous rectifier, okay? This is actually off time. So the off time was calculated to be 20%, right? So that's right here, 20%, right? And then frequency is 80%, 80 kilohertz. 80 kilohertz. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, something like that. Do I have the plot? Yeah. From above plot, 80 kilohertz intersects 20%. at 10 nanofarad. Is that the case? Is that true? So 20% is right there. 80 kilohertz is 2, 3, 4, 5, 6, 7, 8. Right there. What is that? Oh, wait, am I wrong? Oh, 80 kilohertz right here, right? It's 10 kilo, my bad. 10, 20, 30, 40, 50, 60, 70, 80. Right there. So about what nanofarad is that? It is 10, okay, I thought I put 4.7. You can see from here, it is 10 nanofarad, right? So 10 nanofarad capacitor, right there. Next, the timing resistor is found from the following plot. Again, it's provided in the data sheet. So for 10 nanofarad, which is right here, that's the plot for 10 nanofarad, right? And what was the frequency again? 80 kilohertz, right? 2, 3, 4, 5, 6, 7, 8, right there. Oh, no, right there. So what resistor is that? What did I put? About 2 kilo ohms. Is that right? 10 nano is right here, my God, my eyes. 10 nano is this curve right there. 8 would be right here, right? That's 8 kilohertz, 80 kilohertz. So that gives us about 2 kilo ohms, right? Resistors. So that's what I have right here as well, 2 kilohertz. So therefore, for this example, if you want to provide 20% of time, they call it that time, at 80 kilohertz, then the timing components RT and CT would be 2 kilo ohms and 10 nanofarad, and that's how you would connect it. See, I'm using the VREF right there. That's how you connect the RT-CT, okay, for the UC 1840 family.